Thanks, Ken. So yes, I'm Eric Jensen from NASA Ames Research Center in the Bay Area, and I'm going to talk to you about this ATTREX campaign, which is going on right now here at Dryden, so using this NASA Global Hawk aircraft. So first I'm going to try to give a brief overview of the science, why we're doing this, why it's interesting, at least to us. The focus here is on stratospheric water vapor. Now scientists like to divide up the atmosphere into layers. The lowest layer that we live in is called the troposphere, and the next one above that is called the stratosphere. And the division between them we refer to as the Tropopause. Now it turns out that although this isn't, I think, well known by the public, water vapor is an extremely powerful greenhouse gas. So even though the stratosphere is relatively dry compared to the troposphere, small changes in the humidity of the stratosphere can have important effects on the radiation budget of the planet and climate and the surface temperature. So that's really why we're interested. Water vapor in the stratosphere also affects the ozone layer, which is obviously important to us. And it turns out that NASA satellites over the past few decades have shown that there are significant variations in the stratospheric humidity which we really don't understand. So that's really what motivated this ATTREX campaign. Go to the next one. So we're focusing here on the tropical tropopause layer, and this is really what's important for controlling the water in the stratosphere. And that's because the general circulation of the atmosphere brings air up in the tropics into the stratosphere, across this layer, the boundary between the troposphere and the stratosphere, the tropical tropopause layer, and then the general circulation spreads that air throughout the tropics, and it comes down in the polar regions. Now it turns out this tropical tropopause layer, or TTL as we like to call it, is extremely cold. It's one of the coldest places in the Earth atmosphere system, and as a result it acts like a cold trap. So ice clouds form there, and the vapor condenses on those clouds and they fall out, leaving behind very dry air getting into the stratosphere. So really to understand what controls the humidity, we need to make measurements of these clouds, understand the transport and the radiation field. And ultimately what we expect to come out of this is improved fidelity of predictions of future climate change by improving the models. Okay, so we're using the NASA Global Hawk unmanned aircraft, which turns out to be ideal for this problem for a few reasons. One is it's a high altitude aircraft. There are very few aircraft that can reach the tropical tropopause region we're interested in, which is about 10 miles high. The Global Hawk flies up to 65,000 feet, whereas commercial aircraft never get higher than about 45,000 feet. And then the real big unique thing about this airplane is its duration. It's a drone, and so it can fly for a very long time, 30 hours, whereas manned aircraft, especially the high altitude aircraft we've used in the past, have much shorter durations, typically 5 to 7 or 8 hours. So this long range allows us to sample vast regions in the tropics. And I've shown at the bottom here that on a flight here from California, we can fly all the way out to near Guam and come back without landing or refueling. So it really allows us to sample large parts of the atmosphere. Okay, next. So what we've done is as Ken said, we've loaded this aircraft with very cutting-edge, high-tech instruments to measure things like the water vapor under very cold, dry conditions. And we measure a slew of chemical tracers which tell us where the air came from and how it got there, and things like temperature and winds and the radiation fields. And for example, one of these water vapor instruments fires a laser out the side of the aircraft and reflects off a reflector on the wing, and they measure the absorption by water vapor in that path, and it becomes a very sensitive way of measuring water, so we can get the measurements even though it's very dry. Next. So I've been involved in airborne science for a long time, a lot with the DC-8, where, as Ken said, we've got 50 scientists on the airplane with their instruments. This is very different. It's an unmanned aircraft, so we're sitting here in this control room here at Dryden. It's like a mini version of Johnson Control you've seen in movies for spaceflight missions. So there's a front room where the pilots sit, and that's basically considered an active cockpit, so we are not allowed to bug them. And then there's a glass partition, and and all the scientists sit in the back, and so we can be chaotic and making lots of noise without bothering the pilots. And the exciting thing is we have a high-speed internet connection from the plane, so we're getting real-time data from all these instruments into the control room. And there's stations there for each of the instruments, and we can see the data and decide where to send the plane next. People can make adjustments to their instruments to optimize them for the conditions we're flying in. And it turns out it's very interactive and also very exhausting. We've been doing 24-hour flights, and so your human inclination is to try to stay there the whole time. And it's fun to watch people start to collapse in the wee hours. We go to the next one. So again, this is one of these real-time data products we get. We've got an instrument called a LiDAR, which is basically a laser firing down, measuring the backscatter from clouds below. So it's like a radar on the plane looking down. And so as the plane flies along, we get this picture of the clouds below the aircraft, and we can decide where to dip down into the clouds and sample them. One of the things we're looking at is these, what we call subvisible cirrus, this thin layer right up at the top there. It's very high altitude, thin clouds. We call them subvisible because if they're the only clouds, you sit out there in the tropics, it'll look like a beautiful clear sky day. We send the aircraft up there, and it turns out there's this cloud layer covering the entire sky. All right, next. Okay, so this is a typical flight plan that we're going to use for these flights this winter. And so I've shown here on the top a map. So we fly out of California here, go all the way down to the equator, and then go over, fly down south of Hawaii. And then the bottom is a sort of an altitude time curtain. So you can see we have the plane go up and down here between about 45,000 and 65,000 feet. And again, we're sampling this extremely cold air that acts as this cold trap. Some of the coldest air, it basically gets down to a minus 120 Fahrenheit or a minus 90 centigrade, so it's twice as cold as anywhere on the surface. And so if we go to the next one, again, these venture class programs can describe our 5-year programs, which is very nice. We get to go out multiple times. So next year we're planning to take the aircraft to the Western Pacific. We're going to try to go to Guam in the wintertime, and then either Australia or Kadena, which is Okinawa, in the summertime. And these are range rings of the aircraft. These are actually only 8-hour range rings, which means we can fly from these bases out to these range rings, sample for 8 hours, and still fly back. So it's just, again, a really nice thing with the Global Hawk. So next one. So ATTREX is a very multi-agency international program. Actually, we've got instrument teams from NASA, from NOAA, from multiple universities, private companies. In addition to one of the instruments is run by a team from Germany. So we're really excited about this. We've known for some time this is an important part of the atmosphere to sample, and we're very excited about having the opportunity to make these measurements and study the tropical Tropopause region. So I'll be happy to take any questions. Yeah.
I'm sorry if I missed this. So the more water vapor there is in the atmosphere, what exactly does that mean? Okay,
so water vapor is a greenhouse gas, so it acts sort of like CO2 and methane, and so it absorbs the thermal radiation coming up from the planet and re-radiates some of it back down, so it acts like a blanket. So if you increase the water in the stratosphere, you're going to increase the surface temperature. And again, it turns out even though there's not a whole lot of water there, small changes turn out to be actually important for the climate. Yeah.
The subvisible cirrus clouds, how much water and how much effect? I assume that's kind of a recent discovery. That
it's sort of in the satellite era.
How significant is the water that's there? Is it kind of the dark matter of the atmosphere?
Well, it's again, it's very little water compared to what is sitting around us down here in the surface. But it's partly because it's very cold up there, and at the altitude in the atmosphere, that even though there's very little water involved, it is important for the radiation. And it turns out the amount of water is something like 2 parts per million, or 3 parts per million. And there's orders of magnitude more water, factors of thousands more water down here. So it's...
Let's do 1 or 2 more questions, then we're going to have to get running. And you said one of the instruments is run by a team from Germany?
Yes.
Can you tell me which instrument that is?
It's called the Mini DOAS, Differential Optical Absorption Spectrometer. And what we're trying to measure with that is bromine oxide, which is one of these species that destroys ozone. So there's been a lot of uncertainty about how much is up there and how it affects the ozone layer.
And it operates very much like a satellite instrument that's up right now on the NPP satellite.
Thank you.
It does scattering of the atmosphere and looks at the spectrally resolved signal coming back.
So in order to support models and simulations, you guys have to have, I guess, some kind of scheme of data collection in space. And so just talk a little bit about how you work that out.
Well, yeah, the idea here is to combine the measurements we're making with the aircraft with the satellite measurements that Ken described. And it turns out that one of the reasons we're focusing on this part of the atmosphere is it's challenging to make measurements with satellites because things change very rapidly with height. So there's strong gradients in this region.
I guess what I meant was, how are you actually doing that gridding up through the atmosphere? How are you collecting the data through the layers to get that grid of data that then needs to go into, I meant spaces.
Well, it's sort of, again, it requires a combination, because with the aircraft we're making very fine structure measurements in certain altitudes and certain geographic locations. And then we use that in combination with the satellite data to evaluate and improve the models. And again, the data will be available to the entire international community, which, again, as Ken said, is very important. Yeah?
I might have missed, did you say four guys were flying both aircraft at the same time?
No, not for this program. We're just using one of them. The HS3 program is planning to fly both aircraft so they can track hurricanes even longer than 30 hours, over days.
Okay. I was just trying to understand if there were economies of scale with controllers in the room. I know obviously you need two pilots, but if one controller could be working on 2 data feeds at the same time.
I doubt it.
Okay.
It takes a lot of effort, and even for one aircraft, they have 3 shifts for one of these flights, so people don't drop in the front room when they need to be piloting the aircraft. So.